Okay, assalamu alaikum and good morning, guys. Welcome back to grade 11 physics for inspired teens. Well, in today's lesson, we'll be continuing with electromagnetism, right? Okay, sorry for the slight delay. We just went a bit extra with the previous class. But yeah, we'll start probably in the next 2 minutes or so. Let me just get the YouTube link to the group. Okay, cool. I think we can start. Just confirm that you guys can hear me and that everything is working clearly. Okay, perfect. Let's begin. Okay, so before we continue with the last thing that we need to learn and doing some question, let's just do a quick recap of what we learned and what we discussed previously. Okay, so let's just quickly talk about induction of a magnetic field. Okay, so we have two things actually, induction of a magnetic field and induction of an electric current. If we look to the left, we consider induction of a magnetic field. Okay, so this is when we have a current that passes through a conductor, a magnetic field is induced around that conductor. Okay, so if we have a current, magnetic field is created or induced, okay, by that current. Okay, and then we learned about the right-hand thumb rule. So if it's into the page, remember, is away from us. Out of the page is towards us. Okay, so you're going to use your right hand. If you're going to use your left hand, you're going to get the incorrect answer. You have to use your right hand. And if it's out of the page, for example, you point towards yourself, and the direction in which your hands curl is going to be the direction of the induced magnetic field. So let's look at this diagram. Okay, so point your fingers towards you out of the page, the one on the left. You will see that the rest of your fingers curl anti-clockwise. Okay, and that's represented in this diagram. What about into the page? Into the page is point away from you, or like your thumb away from you, and you will notice that your fingers curl clockwise, in the clockwise direction. Okay, then we just discuss this in a loop. Then we can see here, what is this again? Into the page, out of the page. So here we can see it comes out of the page, and there it goes back into the page, and this is what's represented here and here. And here it comes out of the page, Okay, so that's what's represented there. Then we discussed a solenoid. For a solenoid, curl your fingers around the solenoid in the direction of conventional current, and your thumb will point in the direction of the induced north pole. This is known as a right-hand solenoid rule. So yeah, so what you should note is that when we have a solenoid and there's current passing through it, it induces a north and a south pole. So maybe one here and one here, for example. Okay, so depending on the direction of current, so as you can see with the arrows, right, in this case, you just have to understand in which way the solenoid is moving and then follow your hands and try and follow your hands in the direction of current as well as the direction of the wire. So in this case, right, you can see that the wire here is coming from the back, going over and then coming this way. Okay, so in that case here, they're telling us that current is in that direction. So current is coming down here, it is coming from here. Right, so that's how you want to determine it. Sometimes it can be tricky, so please just be careful. Okay, now that goes to the back and comes out on this side. To the back, comes out on that side. So if it's moving in that direction, now we're curling our fingers, right, sort of away from us, right? If you're using it your hands sideways, you're sort of curling your fingers away from you. You select like one of the loops, okay, to indicate that direction to help you. Select one of the loops, curl your fingers over in the direction of current this time. So this time your four fingers, or the rest of it, not your thumb, your fingers represent the direction of current. Okay, so curl your fingers in the direction of current, and your thumb will point in the direction of the induced north pole, the north pole created by this current in a solenoid. Okay, so yes, in this case, it's like you point away from you, you curl over, right? It's moving over, you curl your fingers like that, and then your thumb would point in the right direction, again, which means north pole is here, south pole is there. Okay, let's move on. Let's talk about induction of electric current. When a magnet is brought close to a metal wire, it causes movement of charge in the wire. As a result, an EMF is induced in the wire. Only change in magnetic flux will induce a current. I think this is the most important thing that we picked up from here. Only change in magnetic flux will induce a current. So remember we said that magnetic flux is basically, if we just use a rough informal definition, the amount of magnetic field lines that touch the conductive wire. Okay, there is actually a nice diagram I might get in the middle of the lesson for you guys to have a look at, right? So, so that's what magnetic flux is. Okay, it's how much of the magnetic field lines. So now in this case, remember here we had current first and then magnetic field was created. Here we have magnetic field first and then current is going to be created. So here it's the induction of magnetic field. We create an induced magnetic field, but here it's the induction of electric current. We create an induced current, which in turn creates an induced EMF. Okay, so just keep that in mind. Yes, that's what magnetic flux is. And in order to induce a current, we have to have a change in magnetic flux. We cannot just have flux. Okay, so what does that mean exactly? Remember, we said that if we have a magnet, okay, if we have a magnet and we have the solenoid and this magnet is moving through the solenoid, okay, if it is standing still, there will be no induced current. When there is motion, when this magnet is moving in and out, or it's just moving around it even, okay, moving in any way, as long as it's moving, that's when current will be induced, because when it's moving, there is a change in magnetic flux. Okay, there's a change in the amount of magnetic field lines that are touching this area. Okay, so Faraday's law states that the EMF induced is directly proportional to the rate of change in magnetic flux. So the faster you change the magnetic flux, the higher the EMF basically. Magnetic flux linkage is the product of the number of turns of the coil and the flux through the coil. So those definitions, their formulas are shown here, where we have the formula for EMF, the formula for magnetic flux. Okay, so yeah, then, okay, before we get to Lenz's law, okay. Okay, before we get to Lenz's law, just give me like 2 minutes. I just want to go fetch something to display to you guys, just so that you guys, just to make sure you guys understand, like a makeshift solenoid. Okay, so just give me like 2 minutes or like 3. Okay, I'm back. Let's continue. Okay, just reshare. Actually, okay, let me stop sharing my screen so that I don't know. I don't think I'm going to go full screen on Zoom, but okay, nevertheless. Okay, no, if I stop share, then I should go full screen. Okay, so you guys would be able to see me better now. Let's see which one is. Okay, I think this is better. Okay, you guys should be able to see me full screen so that you can see what I'm trying to explain. So basically the concept that I just want to make sure that you get, okay, is the induction of this electric current. So we have the electron, okay, and this is going to represent our solenoid, okay. So here we have a hollow cylinder, okay, which is going to represent a solenoid. So you can imagine, if you've ever seen a solenoid before, you can imagine that wire is coiled around it. Okay, so this is a solenoid, potentially connected to a circuit. It doesn't really matter, whatever it's connected to. Okay, the main part is that we have this conductive wire, and here we have a magnet. Okay, so it's a bar magnet. Okay, and I'm going to show you with a diagram as well, once I share my screen again, what happens when we move this closer. But let's just say, so you can see that this is hollow, it's a solenoid. And what you want to do is you want to pass the magnet through the solenoid. Okay, that's generally what happens. However, okay, it doesn't have to go through, it can just be along here. But so long as there's motion, okay, so if I hold my magnet here, okay, and if I hold my solenoid here and they both still, there is not going to be, again, this guy is not connected to a battery. That's the main thing. There's no current in the circuit, okay? However, okay, so that's the first thing. Secondly, if I hold my solenoid still and I hold my magnet still, right, there's not going to be any induced current, nothing. The only time induced current takes place, or current is induced, that's better to say, is when I move this magnet. So if I move this magnet in and out and in and out and in and out, okay, that's when current is going to be induced. Okay, again, it doesn't need to move in so long as it's moving. So even if I'm moving it along here, okay, and if I'm not, it's not going into the solenoid, but there's still this change, as as I'll show you in the diagram. When this magnet is moving back and forth, okay, the amount of magnetic field lines that are touching the solenoid is constantly changing. So there needs to be that motion of the magnet in order for there to be an induced current. So maybe sometimes it goes all the way in and then comes to the edge and then comes all the way back, and it constantly moves in and out, right? And remember, Faraday's law states that the induced EMF, the amount of EMF that we induced within this coil, okay, is directly proportional to the rate of change of magnetic flux. So the faster we can change this flux, the rate at which we change it, right, the more EMF we are going to induce. Okay, so I hope that makes sense. That's first analogy. Let me share my screen and we can discuss this in terms of the diagrams where we can actually see the magnetic field lines. Because guys, remember, magnetic field lines are invisible, imaginary lines, right? You don't like actively see them. Okay. Okay, so let's have a look at this diagram. Okay, and this diagram shows us a bar magnet, so similar to what I just had, okay, but obviously now with showing the electric field lines, okay? So showing that those electric field lines, you can see that when the bar magnet is brought close to the solenoid, the bar magnet, the imaginary magnetic field lines around it are automatically there. So when it's brought close to the solenoid, now you can see, okay, this is what we mean by magnetic flux. Okay, it's the amount of field lines that are crossing the solenoid, that are touching the wires of the solenoid. So here you can see it displayed. Okay, we can see these magnetic field lines touching the solenoid, touching the wire. Okay, so let's just say here, both are completely still. Right, none of the solenoid is not moving, the magnetic is moving. They will be, even though there are magnetic field lines touching this wire, there will not be an induced EMF because there needs to be a change in magnetic flux. So a change in magnetic flux, for example, could be represented here. So now this is not going to like move exactly how we want it to, but it's fine. Like it's obviously not going to, it's going to cover it. But here's my magnet. If it's still no magnetic flux, if I move it back and forth, the amount of field lines that are touching this wire constantly change, and that's going to create a magnetic flux. Even better if we move it, and the faster we move it, okay, the better, the higher the magnetic flux. Okay, so I hope that made sense. Okay, then we'll discuss the last thing here, the second last thing. the direction of induced current as a bar magnet moves into a solenoid, the needle of the galvanometer is deflected away from the zero mark. Okay. As the bar magnet is removed, the needle deflects in the opposite direction. The magnetic energy is converted into electrical energy. The direction of induced current can be determined using Lenz's law. Lenz's law states that the induced current the Lenz's law states that the induced current flows in a direction so as to set up a magnetic field to oppose the change in magnetic flux. Okay, so that's important understanding Lenz's law. I'm going to explain Lenz's law with this diagram. I'm going to explain this whole, the key to Lenz's law of opposing the change in magnetic flux. Okay, so basically how you need to remember it is, we have two situations. Okay, we have a situation where the bar magnet is moving towards the solenoid. And we have a situation where the bar magnet is moving away from the solenoid. Okay, so you need to understand that Lenz's law states that the induced current flows in a direction. Okay, so that's not like so key, but anyway, so that to set up a magnetic field to oppose. So this is the key thing. The magnetic field, okay, to oppose the change in the flux. So when it's moving away, so let's just say we have a bar magnet, okay, that has north pole facing, like north pole in the direction of the solenoid. So it's moving away. Keep that in mind. It's moving out. Okay. So in our little analogy, where's my magnet? Okay. We originally had it here, but it's moving slowly. It's moving away. Okay. So when that happens, okay, Lenz's law states that the current, the induced current, okay, will be in the direction such that the magnetic field opposes. So let's just ignore current for now. Let's understand that Lenz's law says that the magnetic field will oppose. Okay, so if it's moving away, the solenoid will want the magnetic field to move towards it. Think of it like that. If it's moving away, okay, the solenoid will try to move the magnet towards it, opposite. So if the magnet is moving away, solenoid wants it to come back. So it will set up its magnetic field in such a way to attract the magnet back. So if it's moving away and north is facing it, the induced south pole will now be on this side because it will attract the north pole of the bar magnet. And of course, south and then the north will be on the other side. Okay, is this making sense? Okay, let's do towards and then we can come back to away. One more time. Okay, let's have a look here. Let's look at towards. Okay, now the bar magnet, again, north pole is facing the solenoid. Okay, but now it's moving towards. So Lenz's law states that the induced magnetic fields will act in a way to oppose that. So because it's moving towards, the solenoid will try to push it away. So it sets up its poles such that it tries to push it away. So in this case, the north pole will be here in order to repel the north pole of the magnet. Okay, let's go through that one more time. Let's look at when it's moving away. When the bar magnet is moving away from the solenoid, it sets up its magnetic poles. So I'm saying it sets up its magnetic poles. How does it do that? By changing its direction of current. When it changes it, when the direction of current changes, the induced poles change as well. So in this case, we have north and south, right? So north and south. Why is induced south pole here and induced north pole here? Because when it's moving away, okay, the solenoid sort of tries to pull it back. So it sets up its south pole there to try and attract the north pole, because remember, unlike charges attract, like charges repel. So it sets up the south to try and attract the north pole back into it. And here, when you're moving it into it, right, it tries to repel it, and then induced north pole is set up there to repel that north pole of the bar magnet there. Okay, and then that actually tells us the direction of current, right? Because now we know where now we need to be able to tell if we have a bar magnet moving towards or a bar magnet moving away. We need to be able to tell in which direction is the induced north pole and induced south pole, and in turn tell the direction of current. So in this case, induced north pole is on the far side. So in order, so remember we use right-hand thumb rule for a solenoid. We point our thumb, so you try this as well with me. Point your thumb in the direction of north pole. So it's like towards your right, let's just say, towards your right. When you point your thumb towards your right, you will notice that your fingers curl towards you, right? And that is indicative here, right? That shows us this direction of current. Okay, it's sort of pointing your thumb towards the right, it's curling towards you and around and around and around. So we can see that the current is actually moving towards that side. Or is it? Okay, it's hard to tell with this one because I can't you don't see the ends of the circuit to see like which direction they're in. Okay, then what about, but we do know one thing, we know that it's clockwise, and here it will be anti-clockwise, right? So we know the direction. Okay. So in this case, induced north pole is towards the left, right? So you point your thumb towards the left and you notice that your fingers will curl away from you, and that's shown here. And therefore it's moving anti-clockwise. Okay, so that's Lenz's law explained. Let's move on to these, not so important, but theoretical aspects of the section. Environmental impact of overhead cables. Birds fly into power lines as they cannot see them from a distance. This places birds at risk of becoming extinct because of the increase in unnatural mortality. Trees fall onto power lines, can cause fires to erupt. Trees have to be cut down to make space for power lines. There is no evidence that the electromagnetic field of power lines has any negative impact on people and surroundings as strength of field is low. The electromagnetic effect of the power line can disrupt radio signals. As for emergency services, this can be a major problem. Okay, let's move on. Let's do some questions. Okay, the solenoid on the left connected to a battery is placed close to the bar magnet on the right, suspended on a light inextensible string and allowed to move freely is shown in the diagram below. Okay, so we have the solenoid connected to a connected to a battery, and a bar magnet is placed close. A light inextensible string and blah, blah, okay, whatever. The bar magnet is on a light inextensible string and is allowed to move freely as shown in the diagram below. So state Faraday's law of electromagnetic induction in words. Faraday's law of electromagnetic induction in words is that the magnitude of the induced EMF across the ends of a conductor is directly proportional to the rate of change in magnetic flux linkage with the conductor. Okay. 6.2, in which direction will the suspended magnet move towards? So in which direction will the suspended move when the switch S is in the circuit of the solenoid is closed, right? Only towards, away from, remains the same. Explain why this will happen. Okay, I want you guys to tell me what do you guys think. Is it going to move towards, away from, or would it just remain the same? You don't have to tell me why, just tell me what you like. Tell me the answer, and then we can discuss it. Okay, towards. Away, towards, away. Okay, I won't say whether you guys are wrong or not. I'll just explain it and then you can see whether you are wrong according to your answer. Okay, so let us go through it now, right? So firstly, because it's connected to a battery, okay, the battery itself is going to create a current in the circuit. Okay, so it's a little bit of understanding of electricity in this question. But there is already current that exists in the circuit due to the presence of the battery, especially because the fact that switch S is closed. Since switch S is closed, you need to remember that current in a circuit travels from the positive terminal of the battery to the negative terminal of the battery. remember it goes behind like that. Okay, so this is the direction in which current is traveling. Okay, since current is traveling in this direction, you have to use right hand thumb rule to determine the induced north and south pole of the circuit. So if you have to use your right hand thumb rule to consider, right, take one of the loops, okay, and use any direction, right, use any direction, use your right hand and consider the direction of current. Now remember, with the solenoid right hand rule, you have to use the direction of current is represented by your fingers, and thumb, the direction of current is represented by your fingers, and your thumb points in the direction of induced north pole. So when I point my fingers in the direction of current, for example, if I consider here, right, that section, and I point it upwards, okay, then I'll notice when I point it up and curl around, that makes sense, right? That makes sense with the direction of current. And when I do that, you will notice that, or I will notice that my thumb is pointing in the left direction. Okay, so when I use the direction of current, I can determine the direction of north pole, induced north pole. So induced north pole is here, induced south pole is here. Okay, if that's not making sense to anyone, let me know. Now, since induced south pole is here and induced north pole is here, remember from what we learned, when the south pole is here and it's the magnet is approaching with the north pole, these are unlike charges and they will attract. So the south pole, so this is not moving, but this south pole will then attract this north pole and it will move towards because of the attraction of south and north. Okay, so that's our answer. Explain why this will happen. So let me just explain what I just did. So why do we explain? I explain? I'm going to explain why this happens. Okay, so firstly, there's current flowing through the solenoid. Okay, current is flowing through the solenoid in such a way, because in this case, there's no way to indicate the direction. Right, we can't really say. Maybe we can say anti-clockwise, but it's not like the way we're facing it, it's not really anti-clockwise, right? So you can say that current is flowing in such a direction that it induces a north pole at A and a south pole at B. Okay, again, the right-hand rule, we use our fingers to indicate the direction of current, and our thumb is going to point in the direction of the induced north pole, okay, which is to the left. And therefore, that's how we know that at A is north pole, at B is south pole. Since B is south pole, the magnet is going to be attracted towards the south pole, and therefore the magnet is moving towards number 6.3. Name 3 changes that can be made to the system on the left to increase the effect of the magnet. Okay, I'll give you 3. Okay, I'll give you a few. We have increase the number of turns or coils on the solenoid. Okay, increase the current. Use a stronger magnet. Okay, so basically those points we discussed earlier. Yeah, I'm not going to give you that last one, but any of these. Okay, these are the ways in which we can increase the immune system on the left to increase the effect of the magnet. Okay, let's have a look at this next question. Okay, yeah, so for those of you who said towards, correct. Towards is indeed correct. Okay, away is not correct, and that's the reason why. Okay, the following diagram shows a solenoid AB connected to a galvanometer, able to record very small currents. The magnet is now moved as indicated. Okay, state Faraday's law of electromagnetic induction in words. The magnitude of the induced EMF across the ends of a conductor is directly proportional to the rate of change in the magnetic flux linkage with the conductor. Okay, 6.2. State what will happen to the reading on the galvanometer when 6.2.1, the magnet is pushed into the solenoid Okay, so there's two. One number 6.2.1 when the magnet is pushed into the solenoid, 6.2.2 when the magnet is held still inside the solenoid. Okay, I want you guys to help me with this. 6.2.1. What will happen when the magnet is pushed into the solenoid? What will happen when the magnet is pushed into the solenoid? Okay, what will happen to the reading on the galvanometer? Remember, the galvanometer is going to be able to read current. So it's going to be able to tell what the current is. What do you guys think? Anyone? Anyone at all? Okay. Okay, true, but I want something a bit different, like a bit more specific. Okay, anyone else? Are you guys awake? Are you guys alive? What happens when the magnet is pushed into the solenoid? Okay, so remember it's outside and now it's going to be moved into the solenoid. What happens to the reading on the galvanometer as it's pushed in? Okay, so I'll tell you. So basically, solenoid will push against the opposite direction. Okay, that's true. Yes, that's true. Okay, but they didn't ask. That's true. Push the current in the opposite direction. Okay. Okay. So let me just rectify like a few things in what you said. So basically, the solenoid will push a current in the opposite direction. So the current is not going to be pushed in an opposite direction. Okay. The induced magnetic poles will oppose this magnet. Okay, so in this case, because it's moving towards the circuit, the solenoid wants to push the magnet away. So how does it do that? If it induces north at A, I'm giving away probably a future answer, north at A and south at B. Okay, if it induces north at A and south at B, north and north, these are unlike charges, so these are like charges, so they will repel each other. Okay, so that is true. The current is then determined accordingly. Okay, then the current is determined according to where the north and the south pole is. Okay, pretend I didn't give you that. This could be north and that could be south. Okay, we'll rectify it at a later point. Okay, so the current is not in the opposite direction. It's just that the magnetic, the north and the south, the induced north and south pole will be induced in such a way that it will oppose the magnet. Okay, and then the current is dependent. The current will be determined thereafter. So depending on where the north and the south pole is, then you can use right-hand rule to determine in which direction your current is going to be. Okay, but yes, it will try to oppose. The magnet can still enter the solenoid. It's just that it will, like when you put two like charges, the two like ends of magnets together, that weird like repelling force, they will like push each other away. That's sort of what will happen. But you can still push the solenoid through to the circuit, right? It's not going to like completely push it away. It's just that the poles are induced in that way, according to Lenz's law. Okay, and someone says the magnetic field lines will change. So that is true. So the magnetic flux will change, not the magnetic field. So it's true, but technically not true. Not the magnetic field lines. Magnetic field lines will not change, because magnetic field lines, it will only change. The type of magnetic field lines or the strength of magnetic field lines will only change when we change the magnet. However, what will change is magnetic flux. Magnetic flux is the amount of magnetic field lines that touch the solenoid. So that's true, right? The amount of magnetic field lines will change. But again, we're not mentioning what is going to happen to the galvanometer. The galvanometer reads current. So because there is a change in magnetic flux, there is going to be an induced current. That's the main takeaway from the 6.2.1. State what will happen to the reading of the galvanometer when the magnet is pushed into the solenoid. The galvanometer will read a current, or there'll be a reading on the galvanometer. Okay, why? Because the magnet is moving into the solenoid, there is motion, there's going to be a change in magnetic flux. And so long as there is a change in magnetic flux, there will be an induced current. And this device measures current. So initially there'll be zero current in the circuit, and all of a sudden the magnet is moved towards it, change in magnetic flux, okay, and therefore an induced current. And therefore what will happen to the reading on the galvanometer? It will increase. There will be a reading present. 6.2.2, you guys answer this for me as well. What will happen if the magnet is held still inside of the solenoid? What happens when the magnet is held still inside of the solenoid? Nothing will change. Okay, true. There will be no current through. Okay, so nothing will change. It's a bit ambiguous. That's a slightly ambiguous, because are you saying nothing will change from the previous answer, or are you saying that the galvanometer is not going to change? The more clear thing to say is that the galvanometer will have no reading. Okay, so someone said that there will be no current. That's correct. Okay, but let's try and be specific to answer the question. They're not asking what will happen to the current, or do you understand, right? They're asking what will happen to the reading on the galvanometer. So even though you are correct to saying that there will be no current, you need to then say, like, there will be no reading on the galvanometer because of no current. Okay, so in the first one, the magnet is pushed into the solenoid. What happens to the galvanometer? There will be a reading. Again, we know that when there is a change in magnetic flux, when the magnet is moving, that's when current is induced. And when the magnet is still, when there's no motion, then there's no current induced, because it takes a change in magnetic flux to induce current, not just magnetic flux. Okay, so when it's held still inside of the solenoid, there's no current. Therefore, subsequently, there is no reading on the galvanometer. Okay, 6.3.1, the magnet is moved into the solenoid. Identify the polarity of point A on the solenoid. Okay, the magnet is moved. Okay, we can discuss this one. Okay, so magnet is inside, South Pole, North Pole. Okay, identify the point A, identify the polarity of point A on the solenoid. Okay, you guys can give your answers quickly. What do you guys think? What would be the polarity of A? Okay, so the solid, okay. I'll wait for one more answer. Okay, the key thing here actually is it's moving towards. That's the main thing. So maybe that hint will help you guys. It's moving towards, right? The magnet is moving towards the solenoid, into the solenoid, right? It's moving from out of the solenoid into the solenoid. Okay, so correct. I think A will be the North Pole. That's correct. Because again, it's moving towards. Okay, so when it's moving towards, we know that it will be set up in such a way to oppose the change. Okay, so North Pole is set up here, okay, to push the North Pole away, and it stays like that. Okay, so it's moving, the magnet is moved into the solenoid, it's moving towards, okay, it's not moved out of the solenoid. When it's moved out of the solenoid, it's moving away. Okay, South Pole, no, not South Pole. Okay, so I hope that explanation makes sense. It's moving into the solenoid, meaning it's moving towards, moving out of the solenoid, moving away. Okay, and then you follow Lenz's law accordingly. Okay, Lenz's law states that the induced current flows in a direction so as to set up a magnetic field to oppose the change in magnetic flux. Okay, so I hope that makes sense. Okay, because it's moving it's because it's moving towards, it will want to push it away. So that's why it sets up the North Pole at A and the South Pole at B. Okay, so identify the polarity of A, north. Indicate the direction indicate the direction that current will flow in the solenoid A to B or B to A. Okay, so now that we know, so the current is always determined by the induced poles. Okay, the poles created at the solenoid. So what do you guys think? A to B or B to A? So now that you know where north is, so let me get rid of this. Now that you know where north is, induced north is, and induced south is, in which direction will current flow, from A to B or from B to A? So remember, your thumb has to point to the left, and then your fingers need to curl. Now this diagram is a bit of a problem. But yeah, the diagrams are a bit weird sometimes, to be honest. Maybe one of the most tricky parts of this section, to be honest, is looking at the diagram. Because, just by the way, right, you see this like link here? This link is supposed to be straight. Those two wires, they like connect with each other. They're not like different. The circuit goes like this. Everything that's in front, I'm going to draw in black. And everything that's behind, I'm going to draw in a different color. Well, let's do blue. And this is like technically on the behind side. And it comes to the front again. And this is behind. It's not supposed to curl, it's supposed to come straight. And then in front again. And then behind. Okay, so yeah, the diagram is a bit of a story. Okay, we have B to A's and A to B's. Okay, so the correct answer is actually A to B. Okay, because so in a solenoid, okay, right-hand thumb rule, pretty sure right-hand thumb rule, right? That's what it's called. No, right-hand solenoid rule. This here is right-hand thumb rule. Right-hand solenoid rule, okay. Your thumb needs to point in the direction of north. Okay, so your right hand is going to point towards your left. Sorry. Your right thumb is going to point towards your left. Right thumb pointing towards left. Not to the right, not to the right, to the left. Okay, and what I would recommend again is take one loop and try and take the front of the loop. Okay, the front of the loop always works easiest. Okay, so you guys are with me, right? Hold up your hand like this and point your thumb to the left. Okay, point your thumb to the left because that's where North Pole is. And I want you to put your hand like here, like these are your four fingers. This four blue lines are like your four fingers. Okay, but now take one of these loops. So we take the first one and pretend your hand is on the first blue one. So I'm going to erase all of this, right? Pretend your hand is on this first blue loop here. Okay. And the loop is going that way, like towards the right. Okay. Now your thumb is pointing towards the left and you are attaching your four fingers here, right? And you, obviously your thumb is pointing towards the left, right? No, not left, right, just left. Okay. Your thumb is pointing towards the left and your fingers automatically would be pointing up when you attach them here, right? Is that correct? Right? When you put your fingers on that blue part, they're going to be pointing up. Then if you curl them around, you'll notice that they curl this way. Okay, and that's the direction of current in which they flow. Okay, so for those of you who said B to A, do you understand why it's not B to A and it's A to B? Because now you can see it's going to go in this direction. So when I'm pointing my thumb to the left, automatically, if I attach the rest of my fingers to that blue part, it's pointing in the upward direction. So if it's moving in the upward direction, it's moving up there and around and around and around and around and around until it goes to B. So let's follow it like up there and around and around and around and around like that. Okay, I hope that makes sense. If it doesn't make sense, let me know and I'll re-explain it. Okay, so yes. Okay, so that's how you work it out. So it's a bit tricky, but the key is to understand the diagram and how the diagram works. So you need to look at the diagram visually, and even if you want, like, confirm with your teacher to help them tell you like exactly how this diagram should be shaped. But again, this diagram was a bit of an issue because these are not connecting, so it kind of looks weird. Right? These should be straight lines, like they're connecting to each other. Okay. Actually, now this looks worse because it kind of looks like it's in front, but it's not in front. This blue part is in front. Okay, so you kind of take one loop at a time, and that's how you try and work it out. Okay, so point your thumb to the right. When you attach the rest of your fingers here on this blue line, you will notice that your fingers point in the upward direction, right? And that shows you, okay, it's going up. At this point here, it's going up. The current is going up. And that gives you answer already, because if it's going up here, okay, then it's going up, down and around, down and around, down and around, and so on. And then that shows you, okay, it's moving from A to B. Current is moving from A to B. Okay, explain the rule and how you use it to get your answer in 6.3.2. So the rule is the right-hand rule for solenoids. The thumb of the right hand will indicate the north pole. So the direction of your thumb will indicate north pole. And the fingers of the right hand will indicate the direction of current flowing in the solenoid. Okay, let's end it there. We won't do this question. When we return next week, we can continue this. I'll just finish up this question. It's not very long. And I'll continue with, we're probably going to start chemistry next week. Atomic combination and intermolecular forces and so on. Okay, so yes. Okay, cool. But let's end it there. I want to end it quickly before I get load shedded at 10. Thank you guys so much for joining. I will see you guys next week. Just a second. But yeah, for those of you who didn't join the first lesson, please make sure you probably want to watch the first lesson and then come back and rewatch this lesson if you are confused or if you are lost. Okay, but yeah. Thank you guys so much for